Hello and welcome to Chapter 15 homework questions. So jumping into the conceptual questions, first of all we want to describe the tea kettle. So the deal with the tea kettle, there is heat transfer, conducting heat from the burner through the metal of the kettle into the water. The water has convective currents to heat the water evenly. And then there's always radiation. You can kind of see the red burner in the color picture. So there's radiating heat. And just the water and the kettle all being above 0 degrees Kelvin, there is some radiation of heat. In this case, I'm assuming that this is a whistling tea kettle, and that the work being done is forcing the steam through that whistle spout, making it whistle. And there's your deal. The internal energy has to be replaced. If you took that kettle off the burner, it would stop converting the water into steam. So the work being done is the steam making the whistle go. The kettle maintains its internal energy by constantly taking in more heat from the burner. Number 13, we have that PV plot, A, B, C, F, A, B, D, E, A, B, C, D, E, F. And the question is asking us about the net work. The net work, the total sum of all the work, positive and negative, around any closed loop is going to be 0. We're going to return to the same place. On a PV plot, any position is a state function, so that's the same temperature. So this gas that has a pressure of whatever and a volume of whatever and a temperature of whatever is going to go through this process and go back to that same point. So the net work done, the input work minus the output work, is going to be 0. And then what is the process also one with the smallest input work required to return to part A? Well, this one would be the smallest input work because it's got less of a pressure difference to overcome, so you'd have to add less heat to return it to its initial position. So there's that. Number 15, with an isothermal process, the problem is that you're putting energy into the system, but you're letting the heat escape to maintain excuse me, a constant temperature. Same deal with isobaric. Isobaric, we generally have the piston moving to change, to regulate so that it's atmospheric pressure on the outside, and there's some mechanical stuff that has to be overcome in order to move the piston. So isothermal and isobaric, constant temperature and pressure, would require time for heat to flow into and out of the system or for the piston to move to regulate it. Isochoric, that's a case where it's constant volume. If I have the stainless steel container, I can do all sorts of things and the volume will stay the same, unless I put in so much pressure or so much heat energy that I blast through the sides of the container. So I don't have to worry about time so much with that process. If the container's strong enough, we'll be okay with that one.